For more than a century, one metal has quietly carried the theme-adorned world on its back. Copper. Every power grid, every data center, every phone charger, every internet cable running along the ocean floor. It's so deeply woven into everything we build that most people never even think about it. Copper is just there, doing its job, like water flowing through pipes. But right now, something is shifting. Artificial intelligence has grown so powerful that the systems running it are hitting a wall. The chips can think faster than the wires between them can deliver information. The cables themselves are becoming the bottleneck. And one country has been racking up an unusual number of breakthroughs in exactly the area needed to break through that wall: China. Over the past few years, Chinese research teams have announced progress in light-based chips, glass-based communication materials, hollow-core fiber, and ultra-fast networking gear. Each piece of news on its own sounds like an interesting science story, but together they point towards something much bigger. What if the future of computing doesn't need copper at all? What if information stops traveling as electricity through metal and starts traveling as light through glass and air? That wouldn't be a small upgrade. It would be one of the biggest shifts computing has seen in a long time. The story here isn't just about a new material or a faster chip. It's about how artificial intelligence is forcing engineers to rethink ideas that have stayed essentially unchanged for over 100 years. The metal that built the modern world may be meeting its match, and its replacement is something you can't even touch. But to understand how we got here, you first need to understand why copper started running out of room. The metal that built everything. Copper has been part of human life for thousands of years. Ancient people used it for tools and jewelry because it was soft enough to shape, but strong enough to hold its form. The real turning point came when people figured out how to send electricity through it, that transformed copper from a useful metal into the literal foundation of modern life. Think about your own home. Behind every wall are copper wires carrying electricity to your lights, your fridge, your TV, your phone charger. Outside, thicker copper cables carry power from plants across entire cities. Underground and under the ocean, even more copper wiring connects continents. So a phone call or a website request can travel from one side of the planet to the other in a flash. Copper earned this role because it's excellent at carrying electricity. Electrons flow through it easily with little resistance. It's also tough, bendable, and fairly abundant compared to other conductive metals like silver, which performs even better but costs far too much to string across an entire country. For more than a century, copper has simply been the obvious choice. Nobody seriously considered replacing it because nothing else offered the same balance of speed, reliability, and low cost. Inside computers, copper plays an even more precise role. Shrink down and walk across a circuit board, and you'd see tiny copper pathways etched into the surface, connecting the processor to memory, memory to storage, storage to network hardware. Every piece of information moving inside your computer travels along those tiny copper roads. For decades, this system worked beautifully. Engineers made the copper paths smaller and better, increased the speed of the electrical signals traveling through them, cut down on interference, and improved signal quality. Every few years, computers got faster, and copper quietly carried the extra load without much trouble. But something started to change when artificial intelligence arrived. AI doesn't use computers the way older software did. Older programs handled information in small bursts. A web server gets a request, sends a response, waits for the next one. A video app sends data to your screen, then sends more when the buffer runs low. These tasks needed speed, but they were predictable and manageable. Artificial intelligence works completely differently. Training a modern AI model requires thousands of chips working together as a single giant machine, with every chip constantly sending huge amounts of information to every other chip, not in small bursts, but in a non-stop flood. Imagine coordinating a 10,000-person project where everyone is working and sharing results simultaneously. Even if every person thinks incredibly fast, the project still slows down if messages can't move fast enough between them. That's exactly what's happening inside modern AI data centers. The chips themselves are astonishingly fast, capable of math at speeds that would have seemed impossible just a few years ago. But the copper connections between them are struggling to keep up. Electrical signals generate heat. Higher speeds use more power. Longer distances weaken the signal, meaning you need extra equipment to boost it before it can continue. As AI systems grow larger, these problems compound. Engineers have spent years improving copper connections and made real progress, but there's a growing sense they're approaching a hard limit. You can only push so much electricity through a copper wire before heat, interference, and power consumption become unmanageable. It's like widening a road through a crowded city. You can add lanes, but eventually you run out of space. The copper road is getting crowded, and AI traffic is growing faster than anyone expected. This is exactly why one country has been racing to find a way around that limit. China has been quietly building an entirely different approach to moving data, one that doesn't rely on pushing more electricity through metal at all, when processors outpace their connections. To understand why the copper road is getting so crowded, it helps to look at what changed inside data centers. For most of computing history, building a bigger system meant buying a faster chip. If your old computer was slow, you upgraded the processor. If a data center needed more capacity, it installed faster servers. Communication between those servers mattered, but it was never the main headache. Servers handled requests, sent responses, and repeated the cycle millions of times a day. Then artificial intelligence arrived and flipped that logic upside down. The biggest AI systems don't rely on one chip doing one job. They rely on tens of thousands of chips working together as a single giant brain. The math happens inside each chip, but the chips must constantly share results with every other chip to keep learning. If one chip finishes its work but has to wait for data from another chip before continuing, it sits idle, and idle chips in a massive AI cluster are extraordinarily expensive. Here's where the problem scales up in a way that catches people off guard. Add more chips, and you don't just add more computing power, you also add more cables, more connections, more complexity. More hardware means more electrical interference between cables. Higher data rates generate more heat. More heat requires bigger cooling systems. Bigger cooling systems consume more electricity. More electricity means higher operating costs. At some point, engineers hit a wall where adding more chips barely improves performance because the network can't handle the extra flow. Think of it this way. You could build the most powerful factory in the world, but if the delivery trucks carrying materials in and out are stuck in gridlock, the factory sits idle. The machines are ready to work, but they have nothing to process. That's what's happening inside AI clusters. The chips are the factory floor. The copper connections are the gridlocked delivery trucks. This creates a strange situation. Companies can spend hundreds of millions of dollars on the most advanced chips available, only to discover those chips spend a large share of their time waiting for data. The bottleneck isn't computation, it's delivery. Every second of idle time represents wasted money, wasted electricity, and lost potential. This isn't a problem you can fix by simply building a better chip. It's a problem with the entire way data moves. For decades, progress in computing followed a simple pattern. Engineers built faster processors, added more memory, improved manufacturing, shrank transistors. Each new generation delivered more performance without changing the overall architecture. You didn't need to rethink how computers worked, just build better parts. Artificial intelligence has broken that pattern. The real challenge now is making thousands of chips act like one synchronized system, like a construction crew building a skyscraper, where every worker is skilled. But if blueprints and materials don't arrive at the right time, the whole project stalls. Timing and coordination become just as important as individual skill. This is why engineers increasingly describe AI infrastructure as a communication problem rather than a computing problem. The question is no longer just which company builds the fastest chip, it's which company builds the fastest system. A complete AI system isn't just a chip. It includes network hardware, memory, storage, power delivery, cooling, packaging, software, and communication pathways. And every single piece has to work together perfectly. If even one layer falls behind, the entire system slows down. This is the wall copper is hitting, and it's exactly the wall a fundamentally different way of communicating could break through. China has been assembling the pieces of that alternative for years. Light instead of electricity. The idea of using light to carry information isn't new. You're already using it every day, whether you realize it or not. Fiber optic cables, which send data as pulses of light through thin strands of glass, already connect cities, countries, and entire continents. When you load a website hosted on the other side of the world, your request likely travels through fiber optic cables laid across the ocean floor, with light carrying your data thousands of miles at remarkable speed. It's been doing this for decades. But here's the catch. Those fiber optic cables connect buildings and cities. Inside the computers themselves, the connections are still made of copper. At some point, the light traveling through the fiber optic cable reaches a data center, gets converted into an electrical signal, and continues its journey through copper wires inside the machines. It's like having a superhighway that suddenly turns into a dirt road the moment you enter the city. What researchers want to do now is bring that superhighway all the way inside the computer, instead of converting light into electricity and back again repeatedly. They want to keep information traveling as light for as much of the journey as possible. Some longer-term visions even imagine light communication working directly between chips inside AI servers, with light carrying information between chips instead of electrical signals running through copper pathways. Light offers several advantages that make this idea appealing. First, it can carry far more information over long distances with very little signal loss. Electricity traveling through copper meets resistance, weakening over distance and requiring extra equipment to boost it. While light traveling through glass or air loses far less energy and can travel much farther before needing any boost. Second, light communication produces far less electrical interference than copper. Pack thousands of copper cables close together inside a data center, and the electrical signals in one can interfere with signals in nearby cables, requiring significant shielding and separation effort. Light doesn't have this problem, and many light signals can travel through the same paths without interfering with each other. Third, because light doesn't create electrical resistance the way copper does, light-based systems can be far more energy efficient, a major factor in AI data centers, where electricity use has become one of the largest costs. Moving the same amount of information using less energy saves money, produces less heat, and shrinks the cooling infrastructure needed to keep everything running. Think of it this way. Copper is like a busy road where cars generate traffic noise and exhaust as they travel. Light is like a train that carries far more people, moves faster, and makes almost no mess. The train doesn't replace every road, but for moving large numbers of people over long distances, it's dramatically better. This is why light communication has become one of the hottest areas of study in modern computing. Engineers are no longer just trying to make copper faster. They're asking whether information should travel in a fundamentally different way, not as electrons flowing through metal, but as light moving through glass and air. This change won't happen all at once. Inside tomorrow's AI data centers, electrical power will still need to reach chips, memory storage, and cooling systems. Copper remains very well suited for delivering power. The challenge isn't electricity, it's information, and for moving huge amounts of data at extreme speeds. Light offers advantages copper simply can't match. China's plan across many fronts over the past several years. Something remarkable has been happening across Chinese research labs, universities, and tech companies. Breakthrough after breakthrough has been announced, each targeting a different piece of the same puzzle. Light-based chips, glass-based chip materials, hollow-core fiber, and ultra-fast networking gear designed specifically for AI workloads. On their own, each piece of news sounds like an interesting lab result. Together, they reveal a coordinated effort aimed at redefining how information moves inside computing systems. Chinese researchers have demonstrated light-based chips designed to handle light signals directly, rather than converting light into electricity and back again, working with light itself as it travels through the system. This removes delays and cuts energy use, representing a fundamentally different approach to chip design. Other research teams have focused on glass-based materials for chip packaging. Traditional packaging materials can struggle with the heat and signal demands of modern AI chips. Glass handles heat better and can support more precise, denser connections between components. It may sound like a minor detail, but in chip manufacturing, the material underneath the chip can matter just as much as the chip itself. Then there's hollow-core optical fiber. Traditional fiber optic cables send light through solid glass cores. Hollow-core fiber, as the name suggests, uses air-filled cores instead, because light travels through air faster than through solid glass. These fibers can transmit data at higher speeds over longer distances with less signal loss. Chinese researchers have reported transmitting data through hollow-core fiber at very high speeds across long distances without traditional signal repeaters, a significant technical achievement. Beyond these specific technologies, Chinese companies have also introduced new networking approaches to reduce delays inside massive AI computing clusters, systems that manage the flow of information between thousands of chips, ensuring data arrives where it's needed with as little delay as possible. The goal is straightforward: eliminate bottlenecks before they become the biggest obstacle to AI progress. What makes China's approach notable isn't any single breakthrough, it's the breadth of the effort. China has invested heavily in light-based research, chip manufacturing, telecom infrastructure, and artificial intelligence over the past decade. These investments have created a network where universities, state labs, tech companies, and manufacturers often work on different parts of the same technical challenge simultaneously. One team improves light-based materials, another advances light-based chips, another designs networking hardware, another builds AI software that can take advantage of faster communication. Together, these advances create momentum that no single breakthrough alone could fully explain. It's like watching different construction crews build different sections of the same bridge from a distance. Each crew seems to be working on its own project, but step back and you realize they're all building the same structure. This also explains why so many recent headlines out of China seem connected: glass-based AI chips, light-based chips, hollow-core fiber, optical networking, high-speed AI links. These aren't separate inventions competing against each other. They're different pieces of a much larger puzzle. And if enough of those pieces come together, future AI systems could look completely different from today's designs. China seems to understand something important about the future of computing. The race won't be won by whichever company builds the single fastest chip. It will be won by whoever assembles every piece together best. Chips, networking, memory, storage, cooling, software, and communication, all working in concert with remarkable efficiency. China isn't betting on one technology, it's betting on the entire system. Whether that system ultimately becomes the world's most powerful remains hard to predict. Companies in the United States, Europe, Japan, South Korea, and Taiwan continue making impressive advances of their own, and competition remains fierce. But the direction is clear, and the implications extend far beyond engineering. It's easy to look at all this and think it's just a story about faster computers, but the ripple effects go much further. Modern artificial intelligence already touches almost every part of the global economy. Healthcare researchers use AI to read medical images and discover new drugs. Climate scientists run detailed models to predict weather and climate shifts. Factories use AI to optimize production lines and cut waste. Banks process enormous volumes of transactions in real time. Self-driving cars rely on AI to make split-second driving decisions. Every improvement in computing speed has effects that ripple across the entire world. Now consider what happens if light communication lets AI systems accomplish far more using less energy. Training times shrink, costs drop, cooling requirements decrease, and more work gets done with the same hardware. A data center that once took months to train an AI model might finish in weeks. A cluster of chips that could previously handle one model at a time might handle several. These aren't small improvements, they're the kind of changes that shift entire industries. Consider the energy angle alone. Data centers already consume enormous amounts of electricity, and AI is increasing that demand every year. Some of the largest AI training runs use as much electricity as a small town. If light communication can cut the energy needed to move information inside these systems, the savings could be substantial. Lower electricity bills, less strain on power grids, smaller physical footprints. These benefits matter not just for tech companies, but for governments, research institutions, and virtually every industry adopting AI. Countries around the world have started treating artificial intelligence as critical infrastructure, not just another software business, investing not only in AI models themselves, but in the factories, supply chains, communication systems, and chip technology needed to sustain progress long term. The country that leads in AI infrastructure gains substantial economic advantages. From creating high-value jobs to attracting investment to setting technical standards, the rest of the world ends up following. China's approach reflects this understanding. Its investments span chip manufacturing, light communication, telecom hardware, AI research, advanced materials, and factory automation. Rather than focusing on one breakthrough technology, Chinese companies and research labs have spent years developing many pieces of the same system simultaneously domestic. AI chips aimed at reducing dependence on imported hardware, expanded memory production, glass materials for better chip packaging, light-based chips, hollow core fiber, and AI networking technology. Each piece addresses a different part of the same challenge. Of course, not every breakthrough reaches the market. Research always involves setbacks. Some technologies take years to become useful, and others may never leave the lab. But the overall direction is becoming increasingly clear. The industry is preparing for an era where moving information becomes just as important as processing it. This is why replacing even part of today's copper infrastructure represents far more than an engineering milestone. It signals a basic shift in how computers are built. For more than a century, moving electricity and moving information relied on many of the same materials. AI is changing that. Instead of asking how to build slightly better cables, engineers are now asking whether information should travel in a fundamentally different way altogether. History offers a useful lesson here. Steam engines eventually gave way to electricity. Vacuum tubes gave way to transistors. Hard drives began sharing space with flash memory. Each of those transitions seemed slow at first. Then sudden, the old technology didn't vanish overnight, staying in use for years, sometimes decades. But the new technology quietly became good enough to solve problems the old one never could, and eventually the new way became the standard. We may be watching the start of a similar transition right now. Not because copper suddenly became bad. Copper remains one of the most reliable, affordable, and widely used materials on Earth. And millions of miles of electrical wiring can't be replaced overnight. But artificial intelligence has created demands copper was never originally designed to meet. The chips got faster, the connections didn't, and when the connections become the limiting factor, the entire design has to change. The future is unlikely to be a world without copper. It's far more likely to be a world where copper and light-based technology each handle the jobs they do best. Electricity will keep flowing through copper. Power delivery will still need traditional electrical wires. But information, the huge non-stop flood of data, artificial intelligence depends on may increasingly travel through light. That difference is becoming more important every year. And if China's current pace of innovation continues, the country could play a major role in shaping what that future looks like. Whether that future arrives in 5 years or 15, one thing already seems clear. The race is no longer only about chips. It's about everything that connects those chips together. In tomorrow's AI world, the fastest chip won't necessarily win. The chip that waits the least will. And if light eventually replaces copper for many of those key connections, we may be witnessing one of the biggest infrastructure shifts in modern computing history. The age of artificial intelligence isn't just creating faster computers, it's creating entirely new ways for computers to talk to each other, and that could change everything.